What is radio astronomy? It's easiest to understand in comparison to regular astronomy. In regular astronomy, you're looking at the sky with either your naked eye or a telescope. In this case, you're seeing visible light, which is a certain wavelength. Radio astronomy is exactly the same, but the wavelength of light is much longer. In our case, it's as much as 300,000 times longer. You might want to look at the radio spectrum for a number of reasons, one of which would be seeing through large clouds of dust and gas that we couldn't see through with the visible spectrum. To detect radio signals at all, we need to use an antenna, like the one on your car when you listen to the radio. For the purposes of this video, I'll draw them like this. The problem here is that throwing up one antenna doesn't let us create a full image of the sky. Since a single antenna doesn't tell us where the signal is coming from, it only lets us listen to it, wherever it might be coming from. To solve this problem, let's add another antenna. Now that we have two antennae, pretend there's a radio source over here emitting radio waves. In radio astronomy, this could be a star, a satellite, or a supermassive black hole at the center of the galaxy. When the radio signals coming from the source reach Earth, they've come a long way, so they arrive at our little antenna setup at parallel angles. Each of our two antennas hears the signal, but notice how the angle the signal arrives at means that the antennas hear the signal at a slightly different time. This time difference between the two antennas hearing the signal is crucial because it tells us a small amount of information about where our radio source might be. Notice how if the radio source was over here and transmitting the exact same signal it was before, the picture looks a little different. Even though the signal reaching both of the antennas is exactly the same, the time difference is now different. We now know that the radio source definitely isn't coming from this angle, since the time difference disagrees with what we heard when we first listened to the signal. Consider that same situation again, but the signal moved along a little bit, like this. In this situation, we've got a bit of a problem, because despite the source being located in a different part of the sky, it's producing the exact same time difference on our antennas. It unfortunately landed exactly one wavelength away from where we first heard the signal. So it's entirely possible that the radio source could be either here or here. Now, keep checking all the spots on the sky and see if they agree or disagree with the time differences that we heard that first time. We're left with this pattern, which tells us that the signal must be coming from one of these spots, but is definitely not coming from these gaps in between them. One of the ways that this situation works with these two antennas is that if you change the distance between the two antennas, and keep the radio signal the same, it changes the possible locations of where the signal might be coming from. So this is all good in 2D, but what about 3D? In 3D, all the same stuff applies, but what we previously had as points where the signal might be coming from now become these lines on the sphere. The star could be here, it could be anywhere on these red lines. While this is a big step up from a single antenna, where we had absolutely no clue where the radio source was, it's still not enough for us to figure out where the source is properly. One location in the sky where we know it is. So let's bring another pair of antennas into the picture and put them on a different angle. This pair of antennas tells us that the star must be located along one of these lines, and this second pair of antennas tells us that the star must be along one of these lines. Putting these two pieces of information together, we narrow down the position for the possible locations of this source to these points where the lines intersect. And with this extra pair of antennas, we're one step closer to figuring out where this mysterious radio source is. But, it takes a lot of pairs of antenna before we know where it is properly. Our radio telescope, called the TART telescope, uses 24 antennas in total. This means that it's got over 200 antenna pairs at its disposal to try and figure out where things are in the sky. It's used to create images like this, or videos like this, which came from a TART in Mauritius. You can think of the TART as a mini radio telescope, which is great for getting started with radio astronomy since it's low cost, easy to build and modify, and open source. If you want your own one, check out our website.